Imagine an object no wider than a typical city on Earth, perhaps 20 to 25 kilometers across. Now, imagine that same small sphere possessing more mass than our entire Sun, which is itself 1,000,000 times larger in volume. This seemingly impossible contradiction is not a thought experiment from science fiction. It is the fundamental reality of a neutron star, one of the most extreme and fascinating objects in the cosmos, representing matter pushed to the very limits of what we understand. These cosmic marvels are not born gently. Their origin story is one of spectacular violence, the cataclysmic death throes of stars far more massive than our own Sun. For millions of years, a truly colossal star, perhaps 10 to 20 times the mass of the Sun, burns brightly, a gigantic furnace in the interstellar void. Deep within its core, a complex hierarchy of nuclear fusion reactions takes place. Initially, hydrogen fuses into helium, releasing tremendous energy. As the star ages and its hydrogen fuel dwindles in the core, helium begins to fuse into carbon and oxygen. This process continues, progressively building heavier and heavier elements, neon, magnesium, silicon, until eventually iron accumulates at the very heart of the star. Each fusion reaction in this sequence releases vast amounts of energy, generating an outward pressure that precisely counteracts the star's immense inward pull of gravity. It is a delicate, long-standing balance, a cosmic tug-of-war that defines a star's entire lifetime, allowing it to shine steadily for millions of years. However, this stellar ballet, this cosmic equilibrium, cannot last forever. The accumulation of iron in the core marks a critical and irreversible turning point. Unlike all the lighter elements, fusing iron does not release energy. Instead, it consumes energy. This means that once the core becomes primarily iron, the stellar furnace loses its ability to generate the outward pressure needed to resist the inexorable force of gravity. The delicate balance, which held for eons, is abruptly shattered. The star, having fought against its own immense gravitational might for its entire existence, suddenly faces an inevitable and catastrophic collapse. It is a moment of profound cosmic drama, where the fate of billions of tons of matter is decided in an instant. What follows is one of the most dramatic and energetic events in the universe, a core collapse supernova. In a mere fraction of a second, the iron core, which at this point might be about the size of Earth, begins to implode. Gravity, now unopposed by the outgoing energy of fusion, pulls the core inward at truly incredible speeds, reaching up to 70,000 kilometers per second, roughly a quarter of the speed of light. The sheer magnitude of this collapse is difficult to grasp. Imagine a region initially hundreds of thousands of kilometers across, shrinking to just tens of kilometers in the blink of an eye. The outer layers of the star, still largely unaware of the catastrophic failure at the core, continue their own inward fall, adding to the crushing, unimaginable pressure. The material is compressed to densities never before encountered in the star's life, far beyond anything imaginable or reproducible on Earth. As the core collapses further, the individual atoms are literally torn apart. The electrons, which normally orbit atomic nuclei, are forced into the protons within those nuclei. This extreme pressure overcomes their mutual electrical repulsion, causing them to merge and transform into neutrons. This fundamental particle transformation is called inverse beta decay. The core effectively becomes a giant atomic nucleus, but one held together by the overwhelming force of gravity rather than the strong nuclear force that binds typical nuclei. The matter becomes so incredibly dense that all the empty space that typically makes up atoms the vast void between the nucleus and its electrons, is squeezed out. A volume of this material equivalent to a sugar cube would weigh hundreds of millions of tons. To put this into a more relatable context, imagine taking all the world's cars, airplanes, buildings, and even Mount Everest itself, then crushing them down until they fit into a single thimble. Even that doesn't quite capture the extreme density of a neutron star. A single teaspoon of this material, if brought to Earth, would weigh approximately 6 billion tons, roughly equivalent to the combined mass of every single living human being on the planet, all condensed into a tiny spoon. This is the exotic state of matter known as neutronium, where the fundamental particles are packed together so tightly that there is virtually no empty space left between them. This rapid, violent collapse continues until the core reaches an astonishing density, roughly that of an atomic nucleus, about 400 trillion times denser than water. At this point, the neutrons resist further compression with immense force, a quantum mechanical phenomenon known as neutron degeneracy pressure. This pressure is so powerful that it effectively halts the inward collapse. The infalling material literally bounces off this incredibly rigid, incompressible neutron core. This sudden rebound generates a powerful shockwave that propagates outwards, tearing through the infalling outer layers of the star. Initially, this shockwave struggles, almost stalling, but it is re-energized by an enormous burst of neutrinos, tiny, elusive subatomic particles, streaming out of the superdense core. These neutrinos carry away a vast amount of energy, helping to push the shockwave outwards, eventually blasting the star's outer layers into space in a brilliant, cataclysmic explosion, a supernova. The supernova explosion is an event of truly mind-boggling scale and energy. For a brief period, often just a few weeks, a single supernova can shine brighter than an entire galaxy of hundreds of billions of stars combined. The energy released in that fleeting moment is staggering, equivalent to the total energy output of our Sun over its entire 10 billion year lifespan, all unleashed in a matter of seconds. It is a cosmic spectacle, visible across vast interstellar distances, forever altering the landscape of its home galaxy. The explosion leaves behind a rapidly expanding, often beautifully illuminated cloud of gas and dust, known as a supernova remnant, which can persist for tens of thousands of years, enriching the interstellar medium with freshly forged heavy elements crucial for future star and planet formation. But at the very heart of this expanding cosmic wreckage, something extraordinary remains. The superdense, city-sized neutron core, the ultimate survivor of this stellar catastrophe, is left behind. This is the neutron star, a compact object that represents matter pushed to the very limits of possibility. Its birth is a testament to the immense, overwhelming power of gravity, a force capable of crushing a star initially hundreds of thousands of kilometers across into a sphere just tens of kilometers wide, yet still retaining its immense gravitational pull. The surface gravity of a neutron star is so extreme that if an object were dropped from a height of 1 meter, it would hit the surface at a speed of over 2,000 kilometers per second, reaching that velocity in just a microsecond. It is a relic, a stellar corpse that, despite its diminutive size, holds an unimaginable amount of mass and energy locked within its incredibly dense structure. This violent origin story establishes neutron stars not just as astronomical curiosities, but as truly ultimate cosmic survivors, testaments to the most extreme processes the universe can muster. They are the collapsed husks of once mighty stars, now existing as the densest known objects in the universe, second only to the enigmatic black holes. Their very existence challenges our understanding of matter and gravity, offering a natural laboratory for physics under conditions we can never replicate on Earth, pushing the boundaries of our knowledge about the fundamental nature of reality. Having witnessed the cataclysmic birth of a neutron star from the heart of a dying giant, we are left with an object almost beyond comprehension. It is a stellar corpse, perhaps only 20 kilometers across, the size of a modest city, yet containing more mass than our entire sun. This incredible disparity in size and mass means that the neutron star is made of material unlike anything we typically encounter. Its density is so extreme that it fundamentally challenges our understanding of matter itself. To truly grasp what a neutron star is, we must delve into the physics that allows matter to exist in such an impossible state, exploring the strange substance known as neutronium. Normally, the atoms that make up everything around us are mostly empty space. A tiny, dense nucleus sits at the center, surrounded by a vast cloud of orbiting electrons. These electrons, though tiny, take up considerable room and resist being squeezed too closely together. This resistance is a fundamental quantum mechanical principle known as electron degeneracy pressure. It's the force that prevents ordinary matter from collapsing under its own weight, and is what supports white dwarf stars, the remnants of less massive stars than those that form neutron stars. In a white dwarf, the electrons are packed as tightly as possible, creating a dense but still recognizable form of matter. However, in the core of a star far more massive than our sun, during the final moments of its life, gravity becomes an overwhelming force, far exceeding anything experienced on Earth. When the star's nuclear fuel runs out and fusion ceases, there is no longer outward thermal pressure to counteract the crushing inward pull of gravity. The core collapses with terrifying speed, shrinking from a size larger than Earth to just tens of kilometers in mere milliseconds. This collapse is so violent and the gravitational pressure so immense that it completely overwhelms electron degeneracy pressure. The electrons are no longer able to resist the squeeze. Instead, they are forced into the nuclei, specifically into the protons. Imagine for a moment the incredible pressure needed to achieve this. Under normal conditions, protons and electrons are stable, distinct particles. But during the core collapse, the conditions are anything but normal. The gravitational force is so intense that it literally crushes the atomic structure. Protons and electrons combine in a process called electron capture or neutronization. Each proton absorbs an electron and transforms into a neutron, simultaneously releasing a tiny, almost massless particle called a neutrino. These neutrinos carry away a huge amount of energy, contributing to the supernova explosion. But the key outcome for the core is the creation of an almost pure sea of neutrons. This new state of matter, predominantly composed of neutrons, is what scientists refer to as neutronium. It is not truly an element in the traditional sense, but rather a bulk material where the individual identities of protons and electrons have been largely dissolved into a collective of tightly packed neutrons. Once formed, these neutrons also resist further compression, but through a much stronger force, neutron degeneracy pressure. Just like electrons, neutrons are fermions, meaning no two identical neutrons can occupy the exact same quantum state. This fundamental rule of physics dictates that they cannot be squeezed arbitrarily close together. It is this powerful neutron degeneracy pressure that finally halts the catastrophic gravitational collapse, preventing the neutron star from shrinking further and becoming a black hole, at least for objects within a certain mass range. To truly appreciate the mind-bending density of neutronium, let's consider a common analogy: a teaspoon of neutron star material. On Earth, that amount would weigh approximately 5 to 6 billion tons. To put that into perspective, imagine a teaspoon holding the combined weight of all the cars, trucks, buses, and trains on the planet, or perhaps a small mountain range. All of that mass compressed into a volume no bigger than your thumbnail. It's a density so extreme that if you were to somehow place a teaspoon of it on Earth, it would instantly punch through the ground, sinking to the planet's core and continuing right through, accelerating out the other side if it didn't first vaporize everything in its path with its immense gravitational pull. This incredible density also means that a neutron star is, in many ways, like a giant atomic nucleus. The density of an atomic nucleus is typically around 2 x 10^17 kilograms per cubic meter. A neutron star's average density is of the same order, about 4 x 10^17 to 6 x 10^17 kilograms per cubic meter. The difference, however, is crucial. An atomic nucleus is held together by the strong nuclear force, which only acts over incredibly short distances. A neutron star, on the other hand, is held together by gravity, which, despite being the weakest of the fundamental forces, becomes dominant when dealing with such immense masses and densities. Despite its uniform appearance from a distance, a neutron star is not a homogeneous ball of neutronium. It possesses a complex layered internal structure, each layer representing matter pushed to different extremes of pressure and density. Moving from the surface inward, we encounter distinct regions, each with unique properties, though much of the very deepest core remains a subject of intense scientific debate. At the very surface of a neutron star, one might find an incredibly thin atmosphere. This atmosphere, perhaps only a few centimeters thick, is composed of residual hydrogen, helium, carbon, or iron atoms that haven't been completely neutronized or expelled during the supernova. Despite its thinness, it is scorching hot, often millions of degrees Celsius, due to the energy released during its formation and the star's slow cooling. Below this tenuous gas lies the outer crust, a solid, crystalline lattice of heavy atomic nuclei. These nuclei, still recognizable as elements like iron or nickel, are highly neutron-rich, meaning they have many more neutrons than protons compared to stable isotopes found on Earth. Interspersed within this lattice is a sea of highly relativistic electrons, electrons moving at speeds close to the speed of light, which still provide some pressure, but are nowhere near as dominant as in a white dwarf. This crust is incredibly rigid, far stronger than steel, and is believed to cause starquakes when the star's rapid rotation or magnetic field causes stresses to build up and then release. As we descend deeper into the inner crust, the pressure and density continue to climb. Here, the nuclei become even more neutron-rich, so much so that they can no longer hold on to all their neutrons. Some neutrons begin to drip out of the nuclei, forming a superfluid ocean of free neutrons, while the remaining neutron-rich nuclei still form a lattice. This neutron drip region is where the transition from atomic matter to neutronium truly begins. The matter here is a bizarre blend of solid nuclei and a fluid of neutrons, sometimes described as nuclear pasta, due to the predicted shapes the nuclei might take: long rods, sheets, or even bubbles, under the extreme forces. These shapes arise from the competing forces of nuclear attraction and Coulomb repulsion. Below the inner crust lies the outer core, the region where the vast majority of the neutron star's mass resides. This is the realm of true neutronium. Here, the density is so immense that individual atomic nuclei have largely dissolved. The matter consists primarily of a fluid of neutrons, along with a small percentage of protons and electrons, typically less than 10% each. What makes this fluid particularly exotic is that both the neutrons and the protons are believed to exist in a superfluid state, while the electrons are superconducting. Superfluidity is a quantum mechanical phenomenon where a fluid flows without any viscosity or friction, allowing it to move perpetually. Superconductivity is a similar state where electric current flows with zero resistance. These properties have profound implications for the neutron star's behavior, particularly its rotation and magnetic field. Finally, at the very center of the neutron star lies the inner core. This is the most mysterious and least understood region. The densities here are truly unprecedented, reaching several times the density of atomic nuclei. What kind of matter can exist under such conditions is one of the most significant open questions in astrophysics and nuclear physics. There are several competing scientific explanations. One possibility is that the inner core is simply a denser version of the outer core, a fluid of neutrons, protons, and electrons, perhaps with some more exotic particles like hyperons, baryons containing strange quarks that become energetically favorable at these extreme densities. However, other theories propose far more exotic states of matter. Some scientists speculate that the neutrons themselves might break down into their constituent quarks, up and down quarks, forming a quark-gluon plasma, similar to what existed in the very early universe just after the Big Bang. Even more speculative is the idea of strange quark matter, where up, down, and strange quarks exist in a stable self-bound state. This would imply that the neutron star's core is not made of neutrons at all, but of a fundamentally different kind of matter. The exact equation of state, the relationship between pressure, density, and temperature for matter in the inner core remains unknown, representing a frontier of fundamental physics. It's a challenging problem because it involves quantum chromodynamics, the theory describing the strong nuclear force, under conditions that cannot be replicated in any earthbound laboratory. The study of neutron stars, therefore, serves as a natural laboratory for exploring the limits of matter and gravity, from the rigid, crystalline crust to the enigmatic, potentially quark-filled core. These cosmic survivors offer a unique window into fundamental physics, allowing us to test theories under conditions that are simply unattainable anywhere else in the universe. Understanding their internal structure and the nature of neutronium is key to unlocking some of the deepest secrets of the cosmos. Having explored the unimaginable densities and exotic states of matter within neutron stars, the question naturally arises: how do we know these incredible objects even exist? For decades, they remained theoretical constructs, fascinating predictions of general relativity and stellar evolution, but elusive to direct observation. Their small size, even with their immense mass, made them practically invisible across the vast cosmic distances. Yet, the universe, as it often does, found a way to reveal its secrets, not through steady light, but through precise, rhythmic pulses. The story of their discovery begins in the late 1960s at the Mullard Radio Astronomy Observatory near Cambridge, England. A team led by Anthony Hewish was constructing a novel radio telescope designed to study quasars, distant, energetic galactic nuclei, by observing the scintillation or twinkling of their radio signals. This new instrument, spanning an area equivalent to 57 tennis courts, was painstakingly assembled, its thousands of dipoles and miles of cable tuned to detect faint radio waves from the cosmos. Among the research students working on this ambitious project was Jocelyn Bell Burnell, tasked with analyzing the reams of data pouring in from the newly operational telescope. Day after day, Bell Burnell meticulously reviewed the squiggly lines on the paper charts, searching for patterns, for anomalies that might indicate new phenomena. Most signals were easily identifiable as terrestrial interference, human-made noise, or known celestial sources. But in August 1967, she noticed something peculiar. A faint, repeating signal that she initially dismissed as scruff, a bit of unwanted noise. Yet this scruff refused to go away. It was a rapid, regular pulse, repeating with an astonishing precision of exactly 1.337 seconds. Such perfect regularity was unheard of for any known natural astronomical source. The team was initially baffled. Could it be interference from passing cars? Or perhaps a secret military signal? Every terrestrial explanation was systematically investigated and ruled out. The signal came from a fixed point in the sky, consistent with a celestial origin. The joke began to circulate that they had stumbled upon little green men, or LGM-1, the first evidence of extraterrestrial intelligence. It was a brief, playful scientific flirtation with the extraordinary, born out of profound puzzlement. But within months, Bell Burnell discovered 3 more similar pulsating sources in different parts of the sky, each with its own unique, incredibly stable period. This discovery effectively dispelled the LGM hypothesis. It was highly improbable that 4 separate alien civilizations would be broadcasting at similar radio frequencies with such precise, regular timing. The scientific community soon grappled with the implications. What kind of object could produce such a rapid, unwavering rhythm? White dwarfs, the previous candidate for dense stellar remnants, were too large. Their rotation would tear them apart if they spun fast enough to produce millisecond-scale pulses. The only known theoretical object that could withstand such immense rotational forces while being small enough to pulse so quickly was the neutron star. The incredible precision of the pulses was a direct signature of a rapidly spinning, ultra-dense body, and thus the first pulsars were identified, marking humanity's first direct observational evidence of neutron stars. These pulsars act as cosmic lighthouses, sweeping beams of radiation across the cosmos. Imagine a lighthouse on Earth, rotating steadily, its powerful beam visible only when it sweeps directly past your position. A pulsar operates on a similar principle, but on a cosmic scale, and with far more extreme physics. A neutron star, born from the collapse of a massive star, inherits and amplifies its progenitor's magnetic field, squeezing it into an incredibly compact volume. This results in magnetic fields millions to billions of times stronger than anything we can generate on Earth. These intense magnetic fields accelerate charged particles, primarily electrons and positrons, from the neutron star's surface or its immediate surroundings, propelling them outwards along the magnetic poles. As these particles are accelerated to relativistic speeds, nearing the speed of light, they emit highly collimated beams of electromagnetic radiation. While some pulsars emit across the entire electromagnetic spectrum, from radio waves to gamma rays, the earliest and most common detections were made in the radio band. If the magnetic axis of the neutron star is misaligned with its rotational axis, these beams sweep through space like the rotating beam of a lighthouse. Only when one of these beams happens to point towards Earth do our telescopes register a pulse of radiation. The period between these pulses is precisely the rotation period of the neutron star itself. The regularity of these pulses is astounding. Some pulsars are more accurate timekeepers than the best atomic clocks on Earth, gradually slowing down over millions of years as they radiate away their rotational energy. This characteristic stability provides invaluable tools for astronomers, allowing them to precisely measure distances, detect planets orbiting other stars, and even test the predictions of Einstein's theory of general relativity with unprecedented accuracy. The sheer consistency of these cosmic beacons, ticking away with metronomic precision, became the unmistakable fingerprint of neutron stars. But even among these extreme objects, there exist titans, the magnetars, objects where magnetism reaches truly mind-bending scales. While typical neutron stars possess magnetic fields that can be 1 trillion times stronger than Earth's, magnetars push this limit even further, boasting fields of 10^14 to 10^15 Gauss. To put this into perspective, Earth's magnetic field is about 0.5 Gauss. A magnetar's field is so potent that it could erase the data on every credit card on Earth from a distance of half the way to the Moon if we were to somehow transport them. Closer in, at a mere 1,000 kilometers, such a field would distort atoms, turning their normally spherical electron orbitals into needle-like shapes, and would fatally rip apart the molecules within a human body. The energy stored within these colossal magnetic fields is immense, far exceeding the rotational energy of even the fastest pulsars. This stored magnetic energy is the driving force behind the dramatic phenomena observed from magnetars. They are primarily identified as soft gamma repeaters, SGRs, and anomalous X-ray pulsars, AXPs. SGRs are objects that sporadically emit intense bursts of X-rays and gamma rays, sometimes repeating these flares over periods of days or weeks. AXPs, on the other hand, are X-ray pulsars that appear to be isolated, lacking the binary companion typically required to power X-ray emission through accretion. The outbursts from magnetars are thought to be triggered by sudden rearrangements of their super-strong magnetic fields. These fields can become tangled and twisted, building up enormous stress within the neutron star's crust. When this stress becomes too great, the crust can crack in what are known as starquakes, releasing colossal amounts of energy in the form of electromagnetic radiation. Another mechanism involves magnetic reconnection, where twisted magnetic field lines snap and reconfigure, similar to solar flares but on a vastly grander scale. These events can unleash more energy in a fraction of a second than the Sun emits in 100,000 years. One of the most powerful magnetar flares ever recorded, from SGR 1806-20 in December 2004, was so intense that its gamma-ray burst briefly ionized Earth's upper atmosphere, even though the magnetar itself was located some 50,000 light-years away. This event provided a chilling glimpse into the raw power of these cosmic magnetic monsters. Perhaps the most famous and well-studied example of a pulsar is the Crab pulsar, nestled within the Crab Nebula. This nebula, a beautiful expanding cloud of gas and dust, is itself the remnant of a supernova observed by Chinese astronomers in 1054 CE. At its very heart lies the Crab pulsar, a rapidly spinning neutron star that rotates approximately 30 times per second, or once every 33 milliseconds. Its incredible rotational speed and powerful magnetic field generate a relativistic wind of charged particles that energizes the entire nebula, causing it to glow brightly across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. The Crab pulsar is not just a fascinating object in its own right. It is a crucial cosmic laboratory for studying the physics of extreme environments, providing insights into particle acceleration, high-energy radiation, and the intricate interplay between rotation, magnetism, and matter at its very limits. Its consistent, energetic pulses make it a cornerstone of pulsar astronomy and a testament to the enduring power of stellar death. Thus, from the initial scruff on a chart recorder to the spectacular flares of magnetars, humanity has gradually deciphered the signals from these enigmatic objects. These spinning lighthouses and magnetic monsters are not merely distant curiosities. They are powerful testaments to the universe's capacity for creating conditions utterly alien to our everyday experience, yet deeply revealing of the fundamental laws of physics that govern all matter and energy. Their very existence, revealed through their pulsed emissions, opened an entirely new window onto the extreme physics of the cosmos. While individual neutron stars are fascinating laboratories of extreme physics, their true cosmic drama often unfolds when they are not alone. Many massive stars are born in binary systems, pairs that orbit each other. If both stars are massive enough, they can both evolve to become neutron stars, leaving behind a compact binary system. Two neutron stars locked in a gravitational dance. These binary neutron star systems are among the most extraordinary phenomena in the universe, destined for a cataclysmic collision that sends ripples through the very fabric of space-time. Imagine two city-sized objects, each containing the mass of more than one sun, orbiting each other at incredible speeds. Over billions of years, these cosmic dancers slowly spiral inward. This spiral is not random. It is driven by a subtle yet profound mechanism predicted by Albert Einstein's theory of general relativity, the emission of gravitational waves. As these massive objects orbit, they accelerate through space-time, creating distortions that propagate outward at the speed of light. These gravitational waves carry away orbital energy, causing the stars to inch closer and closer, their orbital period gradually shortening, their velocities increasing. The final stages of this cosmic ballet are nothing short of spectacular. As the two neutron stars approach each other, their orbital period can shrink from minutes to mere milliseconds. They whip around each other hundreds of times per second, their gravitational embrace intensifying to an unbearable degree. The emission of gravitational waves becomes incredibly powerful, a crescendo of space-time ripples that can be detected across vast cosmic distances. The immense tidal forces begin to stretch and distort the neutron stars, pulling material from their surfaces, forming a chaotic, superheated maelstrom. Then, the inevitable collision occurs. This is not a gentle coming together, but a truly catastrophic impact. The two ultra-dense objects smash into each other with velocities approaching a significant fraction of the speed of light. The material is instantly heated to billions of degrees Celsius, and a vast quantity of incredibly neutron-rich matter is ejected into space at extreme speeds, sometimes exceeding 30% of the speed of light. The core remnants of the merger either collapse almost immediately into a black hole or form a hypermassive neutron star, which itself might only survive for milliseconds before collapsing into a black hole. This violent event briefly outshines entire galaxies in gravitational wave luminosity, and for a fleeting moment, it becomes one of the most energetic phenomena in the observable universe. For decades, these events were purely theoretical, a consequence of Einstein's equations. Gravitational waves, predicted in 1916, were incredibly elusive. They are disturbances in space-time itself, stretching and squeezing the fabric of the universe as they pass. detecting them requires instruments of unimaginable sensitivity. This challenge was met by groundbreaking observatories like the Laser Interferometer Gravitational Wave Observatory, or LIGO, in the United States, and its European counterpart, Virgo. These detectors use a brilliant trick. They split a laser beam along two perpendicular arms, each several kilometers long, reflecting the light back and forth with mirrors. When a gravitational wave passes, it minutely distorts space-time, causing one arm to lengthen and the other to shorten by an infinitesimal amount, smaller than the diameter of an atomic nucleus. This tiny differential change alters the interference pattern of the recombined laser light, signaling the passage of a gravitational wave. The scientific community held its breath for years, building and refining these instruments. Then, on August 17, 2017, the universe delivered. Both LIGO detectors, one in Livingston, Louisiana, and the other in Hanford, Washington, along with the Virgo detector in Italy, simultaneously detected a gravitational wave signal. This signal, designated GW170817, perfectly matched the theoretical waveform predicted for the inspiral and merger of two neutron stars. The event occurred approximately 130 million light-years away in a galaxy called NGC 4993. This was not just a detection, it was a revelation. What made GW170817 truly revolutionary was not just the gravitational wave detection itself, but the fact that it was followed almost immediately by a burst of electromagnetic radiation. Just 1.7 seconds after the gravitational wave signal arrived, NASA's Fermi Gamma Ray Space Telescope and the European Space Agency's Integral satellite detected a short gamma ray burst. This near-simultaneous detection marked the dawn of multi-messenger astronomy, where cosmic events are observed across different channels, gravitational waves and various forms of light, providing a far more complete picture than ever before. The follow-up observations were swift and unprecedented. Within hours, dozens of telescopes around the world and in space, spanning the entire electromagnetic spectrum from radio waves to X-rays, were pointed at the location identified by the gravitational wave detectors. What they saw was a new kind of cosmic explosion, a kilonova. Unlike a supernova, which is powered by the radioactive decay of nickel-56, a kilonova is a fainter, shorter-lived transient event powered by the radioactive decay of freshly synthesized heavy elements. The kilonova associated with GW170817 faded rapidly over days and weeks, but its light curve, particularly in the infrared, and its spectral features provided direct observational evidence for one of the most profound processes in the universe, the cosmic forging of heavy elements. This brings us to the concept of cosmic alchemy. While stars like our Sun fuse hydrogen into helium and then heavier elements up to iron in their cores, elements heavier than iron cannot be formed through standard stellar fusion because their creation consumes energy rather than releasing it. For decades, scientists theorized that these heavier elements, including precious metals like gold and platinum, as well as radioactive elements like uranium, were primarily formed in supernova explosions. However, supernova models struggled to fully account for the observed abundances of the very heaviest elements in the universe. Neutron star mergers offer a compelling solution. The material ejected during these catastrophic collisions is incredibly rich in free neutrons, a direct consequence of the neutron star's composition. In this extreme environment, a process known as the Rapid Neutron Capture Process, or RR process, can occur. Imagine an atomic nucleus bombarded by a torrent of neutrons. instead of slowly capturing one neutron at a time and then having time to undergo beta decay, where a neutron turns into a proton, emitting an electron. These nuclei rapidly absorb many neutrons in quick succession. This creates extremely neutron-rich, unstable isotopes. Once the intense neutron flux subsides, these unstable nuclei undergo a series of swift beta decays, transforming their excess neutrons into protons, thereby climbing the periodic table and forming stable, heavier elements. The kilonova observations from GWW 770817 confirm this theoretical framework. The infrared emission detected from the merger remnant was consistent with the decay of newly formed heavy elements, and later spectroscopic analysis hinted at the presence of elements like strontium. The sheer volume of neutron-rich material ejected in a single merger event is staggering. Scientists estimate that a single binary neutron star merger can produce many Earth masses of gold and platinum, along with significant quantities of other heavy elements. This means that the gold in your jewelry, the platinum in your catalytic converter, and indeed many of the heavy elements essential for technology and life on Earth, were likely forged in the heart of these violent, distant cosmic collisions, long before our solar system even existed. The profound implications of this discovery are still being unraveled. It fundamentally alters our understanding of galactic chemical evolution, providing a robust explanation for the observed abundances of the heaviest elements across the cosmos. It suggests that neutron star mergers, rather than supernovae, might be the dominant source for many elements heavier than iron, particularly those at the very end of the periodic table. This new cosmic blueprint for element formation reshapes our view of how the universe builds itself up, from the simplest hydrogen to the most complex heavy metals. It also underscores the interconnectedness of all cosmic phenomena, demonstrating how the violent death of massive stars, the extreme physics of neutron stars, and the subtle ripples of space-time conspire to create the very building blocks of our world. Despite the profound insights gained from observing pulsars and, more recently, from the groundbreaking detection of gravitational waves from merging neutron stars, these cosmic titans remain shrouded in many fundamental mysteries. Humanity has gathered an impressive amount of data, yet the internal structure and precise composition of a neutron star's core, where matter is compressed to densities beyond imagination, still present some of the most challenging puzzles in astrophysics and nuclear physics. It is a realm where our understanding of fundamental forces and particles is pushed to its absolute limits, a true edge of scientific knowledge. One of the central, most vigorously debated topics revolves around the equation of state for neutron star matter. Imagine trying to understand how a material behaves under pressure and temperature, how much it compresses, how much energy it stores, what phase transitions it undergoes. For everyday materials, this is relatively straightforward. We can measure it in a lab. But inside a neutron star, the conditions are so extreme, densities reaching hundreds of trillions of grams per cubic centimeter, pressures immense enough to crush atomic nuclei, that replicating them on Earth is utterly impossible. The equation of state is essentially a recipe that describes how this exotic matter responds to such incredible pressure, and it dictates everything from the star's maximum possible mass to its radius and even its cooling rate. Current theories propose a spectrum of possibilities for what lies beneath the neutron star's crust. As we journey deeper than the outer and inner crusts, where nuclear pasta forms, we enter the outer core. Here, neutrons are no longer bound in nuclei but exist as a superfluid, alongside a small fraction of protons and electrons. But the inner core, typically reaching densities of 5 to 10 times that of an atomic nucleus, is the true enigma. Some models suggest that, at these extreme pressures, even neutrons themselves might begin to break down. One hypothesis posits the appearance of hyperons, particles similar to neutrons and protons, but containing one or more strange quarks. These heavier baryons would further soften the equation of state, potentially leading to smaller, more compact neutron stars for a given mass. Even more exotic scenarios involve a complete phase transition to quark matter. Under such immense compression, the individual neutrons and protons, which are themselves composed of elementary particles called quarks bound together by gluons, might lose their individual identities. Instead, their constituent quarks could become deconfined, forming a sea of free up, down, and potentially strange quarks, moving about freely in what's known as a quark-gluon plasma. This state of matter is believed to have existed in the very early universe, just microseconds after the Big Bang. If quark matter does exist in neutron star cores, it would drastically alter their properties, making them even more compact. A particularly intriguing, albeit speculative, variant is strange quark matter, a hypothetical form of quark matter containing roughly equal numbers of up, down, and strange quarks, which some theories suggest might be even more stable than ordinary nuclear matter. The presence of these exotic phases would fundamentally change our understanding of matter itself. Distinguishing between these competing models is incredibly challenging because they all predict slightly different relationships between a neutron star's mass and its radius. A stiffer equation of state, meaning the matter resists compression more strongly, would result in larger neutron stars for a given mass. Conversely, a softer equation of state, perhaps due to the presence of hyperons or quark matter, would yield more compact stars. This subtle interplay is what scientists are striving to measure. It is also important to clarify some common misconceptions surrounding neutron stars, particularly their distinction from black holes. Both are cosmic remnants of massive stellar deaths and possess incredibly strong gravitational fields. However, their fundamental nature is vastly different. A neutron star has a physical surface and a definite size, typically around 10 to 12 kilometers in radius, supported by the quantum mechanical resistance of neutrons to being crushed further, known as neutron degeneracy pressure. Matter within a neutron star, while unimaginably dense, is still matter. A black hole, on the other hand, is not matter in the same sense. It is a region of space-time where gravity is so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. Inside this horizon, classical physics suggests matter collapses to an infinitely dense point, called a singularity. A critical difference lies in their mass limits. Neutron stars have a theoretical upper mass limit, known as the Tolman-Oppenheimer-Volkoff, or TOV limit, which is estimated to be around 2 to 3 solar masses. Beyond this threshold, even neutron degeneracy pressure can withstand the force of gravity, and the object must inevitably collapse further to form a black hole. Therefore, a neutron star is the densest known form of matter in the universe, whereas a black hole represents a complete gravitational collapse beyond the state of matter, fundamentally warping space-time itself. They are distinct endpoints on the cosmic evolutionary path of massive stars. To unravel these deep mysteries and test the various equations of state, astronomers rely on a combination of precise observations and sophisticated theoretical modeling. One of the leading instruments in this quest is the Neutron Star Interior Composition Explorer, or NISA. Launched in 2017 and installed on the International Space Station, NISA is an X-ray telescope specifically designed to study neutron stars. Its primary mission is to measure the size and mass of neutron stars with unprecedented accuracy. It achieves this by meticulously observing the X-ray emissions from hotspots on the surface of rapidly spinning pulsars. As a neutron star spins, these hotspots rotate in and out of view, causing the observed X-ray brightness to pulsate. The intense gravity of the neutron star, however, warps space-time around it, bending the paths of photons. This gravitational lensing effect allows light from hotspots on the far side of the star to curve around and become visible, even when they would ordinarily be hidden. By carefully analyzing the precise shape of these X-ray pulse profiles, the way the brightness changes over time, scientists can deduce the star's radius and mass. Imagine a cosmic light show where the very fabric of space is bending the light. NISA uses this phenomenon to map the star's surface and infer its fundamental dimensions. These precise mass-radius measurements provide crucial data points that directly constrain the equation of state, helping to rule out some theoretical models and support others. NISA has already provided the most precise measurements to date for several pulsars, including PSR J0030+0451 and PSR J0040+6620, narrowing down the possibilities for the exotic matter within. Looking to the future, the next generation of gravitational wave detectors promises to revolutionize our understanding even further. The groundbreaking detection of GW170817, the merger of two neutron stars, marked not only the dawn of multi-messenger astronomy, but also offered a new window into the extreme physics of these objects. As two neutron stars spiral inwards before merging, the intense gravitational stresses cause them to deform, much like squeezing a rubber ball. This tidal deformability leaves a subtle yet detectable imprint on the gravitational wave signal itself. A stiffer equation of state would mean the neutron stars are less deformable, while a softer one would imply greater deformation. By precisely analyzing the gravitational waveform, particularly during the final moments before coalescence, scientists can extract information about this tidal deformability, providing another independent constraint on the equation of state. Current gravitational wave observatories like LIGO and Virgo are continuously being upgraded, enhancing their sensitivity and expanding their reach across the cosmos. Beyond these, ambitious plans are underway for next-generation detectors. On Earth, projects like the Cosmic Explorer in the United States and the Einstein Telescope in Europe envision vastly larger interferometers, potentially tens of kilometers long, compared to LIGO's 4-kilometer arms, that would dramatically increase the volume of space they can observe and the precision of their measurements. The Einstein Telescope, for instance, is planned as an underground, triangular configuration to minimize seismic noise, pushing the boundaries of terrestrial detection. In space, the Laser Interferometer Space Antenna, or LISA mission, will consist of 3 spacecraft forming a giant triangle separated by millions of kilometers, designed to detect lower frequency gravitational waves from supermassive black hole mergers and early-stage binary neutron star inspirals that would be invisible to ground-based detectors. These future observatories will detect hundreds, if not thousands, of neutron star mergers, providing an unparalleled wealth of data. Each merger will be a unique experiment, allowing scientists to piece together a more complete picture of the equation of state and potentially reveal the presence of exotic matter in the cores of these stars. The interplay between X-ray observations from missions like NICA which probe the surface and overall structure, and gravitational wave detections, which offer insights into the dynamic behavior and deformability of neutron stars during mergers, represents a powerful, synergistic approach. The ongoing quest to understand neutron stars is a testament to humanity's insatiable curiosity and our drive to push the boundaries of knowledge. These cosmic laboratories, where gravity and quantum mechanics clash, offer a unique opportunity to test the very limits of our physical theories. They challenge our models of nuclear matter, provide clues about the fundamental forces governing the universe, and continue to inspire new avenues of research. The next decades promise to be a golden age for neutron star astronomy, with new discoveries poised to reshape our understanding of matter at its most extreme. Our journey through the cosmos has brought us face to face with some of the most extreme objects imaginable: neutron stars. From their violent birth in the heart of a collapsing massive star, through the unimaginable densities of their neutronium cores, to their manifestation as precise cosmic lighthouses and magnetic monsters, these stellar remnants push the boundaries of physics and challenge our understanding of matter itself. They are the ultimate survivors of stellar catastrophe, city-sized spheres packing more mass than our Sun into a volume barely larger than a metropolis, creating a gravitational field so intense that a single teaspoon of their material would weigh billions of tons here on Earth. We have witnessed the dramatic process of core collapse supernovae, where the inexorable pull of gravity overwhelms all other forces, crushing protons and electrons into a sea of neutrons. This extraordinary transformation gives rise to objects supported not by the heat of nuclear fusion, but by the quantum mechanical principle of neutron degeneracy pressure, a force born from the reluctance of neutrons to occupy the same quantum state. This delicate balance allows matter to exist in a state far denser than atomic nuclei, yet still possess a physical surface, distinguishing neutron stars from their even more enigmatic cousins, black holes. These are the natural laboratories where the universe conducts its most fundamental experiments, providing unparalleled insights into the very fabric of reality. The observable universe has revealed these titans to us in fascinating ways. We learned of pulsars, rapidly spinning neutron stars whose powerful magnetic fields funnel beams of radiation across the cosmos, sweeping past Earth with clockwork precision, much like a cosmic lighthouse. Their discovery by Jocelyn Bell Burnell and Anthony Hewish in 1967 marked a pivotal moment in astronomy, opening a new window into the extreme universe. Then there are magnetars, a rare and even more exotic class, wielding magnetic fields so strong they are capable of twisting space-time and generating colossal bursts of X-rays and gamma rays, events that can release more energy in a fraction of a second than the Sun produces in 1,000 years. These phenomena are not just curious observations. They are direct probes of physics under conditions that are literally unattainable anywhere else. Perhaps one of the most profound revelations regarding neutron stars came with the detection of gravitational waves from merging binary systems. The spiraling death dance of two neutron stars, predicted by Einstein's general relativity, culminates in a cataclysmic collision that sends ripples through the very fabric of space-time. The groundbreaking observation of GW170817 by the LIGO and Virgo observatories in 2017 not only confirmed these predictions, but also ushered in the era of multi-messenger astronomy. This single event, followed by a short gamma-ray burst and a kilonova, provided direct evidence that these mergers are the cosmic crucibles where the heaviest elements in the universe, such as gold, platinum, and uranium, are forged through the rapid neutron capture process. This means the precious metals in our jewelry and the heavy elements vital for technology and even life itself owe their existence to the violent embrace of these ultra-dense stars, connecting humanity directly to the most extreme events in the distant cosmos. Neutron stars, therefore, stand as unparalleled natural laboratories for testing the limits of fundamental physics. Their immense gravitational fields provide an exquisite testing ground for Einstein's general relativity, pushing the theory to its breaking point. The precise timing of pulses in binary systems, such as the Hulse-Taylor binary, has already provided some of the most stringent confirmations of gravitational wave emission, decades before direct detection was possible. Future observations of binary pulses with even greater precision will allow scientists to probe subtle deviations from general relativity, potentially revealing new aspects of gravity itself that are not apparent in weaker gravitational fields. The way these extreme objects deform under tidal forces during a merger, for instance, provides a signature in the gravitational wave signal that reveals critical information about their internal structure and the stiffness of their matter. Beyond gravity, neutron stars offer a unique opportunity to study matter under conditions of extreme density and pressure, far exceeding anything achievable in terrestrial laboratories. The equation of state, EOS, of neutron star matter, which describes how pressure varies with density, remains one of the most hotly debated topics in astrophysics. Does the core of a neutron star contain only neutrons, protons, and electrons, albeit in a superfluid state? Or do more exotic phases of matter emerge, such as hyperons, particles containing strange quarks, or even deconfined quark matter, where the quarks are no longer bound within individual neutrons and protons? The answer to this question holds the key to understanding the strong nuclear force, one of the four fundamental forces of nature, which governs the interactions within atomic nuclei. Missions like NISA, the Neutron Star Interior Composition Explorer mounted on the International Space Station, are actively working to constrain the EOS by precisely measuring the mass and radius of neutron stars through X-ray pulse profile modeling. By observing how X-rays from the star's surface are distorted by its immense gravity and rapid rotation, NISA provides crucial data points that help rule out certain theoretical models of the EOS. The study of neutron stars also has tangible, if sometimes indirect, practical significance for humanity. The incredible precision of pulsar timing, for example, is being explored for deep space navigation. Just as GPS satellites provide location data on Earth using highly accurate atomic clocks, a network of X-ray pulsars could serve as cosmic lighthouses for spacecraft traveling far beyond our solar system. This X-ray navigation, or XNAV concept, would allow autonomous probes to determine their position and velocity with extreme accuracy, even across interstellar distances, without relying on continuous communication with Earth. Furthermore, the development of gravitational wave detectors like LIGO has pushed the boundaries of engineering, leading to advancements in ultra-high vacuum technology, seismic isolation, and precision laser interferometry, which have applications far beyond astronomy, from materials science to metrology. Perhaps the most profound practical significance lies in understanding our cosmic origins. The confirmation that neutron star mergers are the primary factories for heavy elements like gold and platinum fundamentally changes our understanding of the universe's elemental composition. Every atom of gold on Earth, in our jewelry, or in our electronics, very likely traveled billions of light years and billions of years from a cataclysmic merger event. This cosmic connection provides a deep appreciation for the dynamic and violent processes that shape the universe and ultimately led to the formation of our planet and ourselves. It inspires a profound sense of wonder and underscores the interconnectedness of all matter. Looking ahead, the next generation of observatories promises to unlock even deeper secrets of these cosmic titans. Next-generation gravitational wave detectors, such as the ground-based Cosmic Explorer and Einstein telescope, and the space-based LISA, Laser Interferometer Space Antenna, will detect thousands of neutron star mergers, providing an unprecedented wealth of data. These instruments will measure the tidal deformability of merging neutron stars with exquisite precision, allowing scientists to paint a much clearer picture of their internal structure and the elusive equation of state. Radio telescopes, like the Square Kilometre Array (SKA), currently under construction, will discover thousands more pulsars, including many in binary systems, offering new opportunities to test general relativity and search for new physics. X-ray and gamma-ray observatories will continue to probe magnetos, seeking to understand the mechanisms behind their powerful flares and the role of their extreme magnetic fields. The open questions surrounding neutron stars are as vast as the cosmos itself. What is the precise maximum mass a neutron star can attain before collapsing into a black hole? The Tolman-Oppenheimer-Volkoff limit is still being refined, and its exact value is crucial for understanding the final fate of massive stars. Do some neutron stars truly harbor exotic matter like quark-gluon plasma, or strange quark matter in their innermost cores? This remains a tantalizing possibility that could revolutionize our understanding of particle physics. How exactly do magnetos generate and maintain their ultra-strong magnetic fields? And what are the full implications of these fields for the surrounding space-time and matter? Scientists are also actively searching for more subtle phenomena, such as continuous gravitational waves from rapidly spinning, slightly asymmetrical neutron stars, which would provide a direct probe of their internal structure and crustal deformations. Neutron stars represent matter at the very edge of possibility, a testament to the universe's capacity for both immense violence and exquisite order. They are not merely astronomical curiosities. They are natural laboratories where the most fundamental laws of physics are tested and revealed. From their fiery birth in a supernova to their role in forging the elements that make up our world, these cosmic titans continue to inspire awe and drive scientific inquiry. As our instruments become more sensitive and our theories more refined, the enduring mystery of neutron stars will undoubtedly continue to unravel, revealing new layers of complexity and wonder in the universe we inhabit. The journey of discovery continues, propelled by the relentless curiosity of humanity, forever seeking to understand the cosmos and our place within its grand, unfolding story.